right, section 3C is on rational functions, and I just in this video want to give you kind of an introduction to what their equations look like and what their graphs look like. All right, so a rational function is a ratio, a fraction, of two polynomials. So I put a polynomial on top and a polynomial on bottom. Okay, so both of those are polynomials. And then the graphs don't look anything like what our polynomials do. When we divide two of them, it gives us something completely different. All right, so I'm going to head over to Desmos and just take a look at a few so we can kind of get an idea of what these graphs look like. And these graphs can look like lots of different things, but we'll just kind of pick some basic ones to get started. All right, so this is the function f of x equals x plus 5 over x minus 3. And it's a couple of features about rational functions. Very frequently, they will be broken into a couple of chunks like this. This one has kind of a left part and a right part. And those two are not connected, even if I zoom out quite a bit. Those two parts never connect. Okay, they're just two arms of the graph. Zoom back in here. There we go. All right, and then also you can kind of see it sort of flattens out to the far right-hand side and the far left-hand side. They're kind of leveling off. They're not going up to infinity or negative infinity on the far left and on the far right. And that's also another thing that frequently happens with rational functions. All right, and then this graph, this one's broken into 3 pieces. Depending on the formula, you might have as many pieces as you want. You could have a rational function with 42 different pieces. It just kind of depends on the formula. All right, and so it has these spots where the graph breaks, and then again to the far left and the far right, you can see this thing sort of levels off and settles down. It looks like it's trying to attach itself to the x-axis there. All right, and then this third one, same kind of thing. This one has 2 parts. It's got a break, and then that flattening off behavior. Okay, and this one has kind of a weird little hump there at around x equals 1.5. Okay, and they don't always behave exactly like those 3. This one's kind of weird. It's got that break, it's got the 2 breaks, but it doesn't really flatten off on the ends. We'll talk about that in a minute. All right, so those breaks in the graph, let's go back to x plus 5 over x minus 3. All right, this one has a break. Let's see. At x equals 3, if I draw a dotted line here, this is the spot where the graph breaks. All right, and if we look at the formula for just a second, we can see exactly why that function sort of freaks out when it gets to that line x equals 3. Okay, because x equals 3 causes division by 0. 3 is not in the domain of that function. All right, so that vertical line is what we call a vertical asymptote. And we write it as the equation of a vertical line, x equals 3. All right, and a vertical asymptote it's not part of the graph. It's not a y-coordinate part of the graph, but it is a barrier for the graph. And a rational function will never cross a vertical asymptote. All right, because it's associated with division by 0. We can never, never, never divide by 0, so you can never, never, never cross a vertical asymptote. All right, and it kind of has asymptotic behavior in the other direction too. If you draw a horizontal dotted line at y equals 1, you can see that the graph is kind of leveling off, or if you turn your head 90 degrees to the left, kind of looks like it's doing the same thing in the horizontal direction that it did in the vertical. All right, so that line y equals 1 that I drew, we call that a horizontal asymptote. All right, and why it's equal to y equals 1, that's a little bit more complicated and not as obvious as the vertical asymptote. So in the next video, I'm going to show you how you can calculate where those horizontal asymptotes are. by looking at the formula rather than trying to guess by looking at the graph. All right, so let's go to the second function and see if we can identify its vertical and horizontal asymptotes. All right, so this one has two vertical asymptotes, all right, and I can kind of look, it's pretty easy to see where they are on the graph at x equals 2 and x equals -2. All right, and both of those values make sense for vertical asymptotes because it looks like, I factored the denominator here for you, it looks like both of those values cause division by 0. All right, so we'll associate vertical asymptotes with division by 0. Okay, so my vertical asymptotes are at x equals 2 and x equals -2. And just solely by looking, not because it's obvious from the formula, we can see that this thing is leveling off towards the x-axis, right? So the x-axis is where the far left and right hand sides are flattening out. So we're going to say that our horizontal asymptote is the x-axis, which is the line y equals 0. All right, and you'll notice that this graph actually crosses its horizontal asymptote there at -1. Okay, so it's important to note vertical asymptotes are associated with division by 0, which is a never, never, never thing. Horizontal asymptotes, again, are not associated with the never, never rule. They're kind of a little bit, anyway, the graph can cross a horizontal asymptote. So you're never going to cross a vertical asymptote, but you could cross a horizontal asymptote. All right, so let's go on to that third graph. Just kind of identify. All right, so the vertical asymptote, again, I'm going to kind of cheat and look at the formula there. The vertical asymptote, let's see, looks like it might be the y-axis, and it is, because x equals 0 is what's going to cause division by 0 in this function. All right, and the graph, the right half of the graph seems to be a little bit closer here to that vertical asymptote than the left, and so it's not necessarily obvious that it's exactly at 0. So I did kind of have to cheat and look at the formula, and then the horizontal asymptote again. Well, let me write that down. The vertical asymptote was x equals 0, and the horizontal asymptote again looks like it's the x-axis. All right, and again, it's crossing that horizontal asymptote here at 1, and it did it again over here at -3, and it's okay to cross the horizontal asymptote. Okay. The horizontal asymptote just really defines where the far right and the far left sides are going. All right. Okay, and then this weird graph at the end, let's go look at that one. This one has a vertical asymptote as expected. All right, again, looking at the formula, that denominator tells us to expect that vertical asymptote at -1, and there it is. All right, but this one does not have a horizontal line. I can't draw my green dotted line to figure out where the horizontal asymptote is. Okay, so while the vertical asymptote was the same as the other ones, not the same number, but kind of the same concept, this one has no horizontal asymptote. Okay, and so some functions just don't have horizontal asymptotes, and that's okay. And this one doesn't. This one actually has what we call a slant asymptote. So I'm just kind of draw it in here for you. Again, there are ways to calculate these. We're actually not going to calculate these slanted asymptotes, but you can kind of see how this guy likes this line, -x + 1. All right, here's a slant asymptote. All right, so I'd encourage you to kind of play around with different formulas on Desmos and just to kind of see what a rational function looks like and how it varies a lot. It doesn't look anything like the graph of a polynomial. It has these asymptotes and very different behavior. All right, next video, we'll talk about how to calculate those asymptotes.